Hi, I'm Dr. J from Modern Statistics. In this video, you will learn how to design and test a hierarchical regression model in SPSS and interpret the output coherently and accurately. I've seen many students often getting confused as to what hierarchical regression is or why one would bother running a regression model in a hierarchical fashion. So my objective in this video is to clearly explain the situation that would require the use of a hierarchical regression modeling and the benefit that you will get by running it that way. And I will interpret the key components in the output that will help you interpret your own results. Let's jump right in. Here I am in SPSS with a dataset that contains 6 variables. This dataset is based on a survey that I conducted and includes a sample of roughly 1,000 workers in the United States. In order to explain why, for example, I would like to run a hierarchical regression model, I first need to show you what we are not getting by running a standard multiple regression, which is to enter all the independent variables at the same time. Now, I have a variable for job satisfaction, which measures how happy a person is with his or her job. And I want to use the 5 independent variables here to see whether they can predict job satisfaction collectively and independently. The independent variables I have here are gender, age of the workers, type of employment, so full-time versus part-time, how long they have been with the organization, and finally, PG fit, which measures how much fit they think there is between themselves and their group or team coworkers. Now, to run the regression from a traditional sense, meaning we enter all 5 independent variables in the model all together, we go to Analyze, and go to Regression and select Linear. Then on the linear regression window, we enter our dependent variable job satisfaction to where it says dependent and enter all our 5 independent variables to where it says independence, like so. Let us click on the statistics button. Here, in addition to what is already selected by default, we'll also select confidence interval, descriptives, part and partial correlations, and collinearity diagnostics. In the residual section, let's select case-wise diagnostics and outliers outside 3 standard deviations and click continue. Now, let us go to the plots button. Here, move standardized predicted values to x-axis and move standardized residuals to y-axis. And under standardized residual plot, select normal probability plot and click OK. And click continue and click on the save button. Select these 2 under distances and click continue. And click OK to run the standard multiple regression procedure. The SPSS output will have about 7 or 8 tables and figures depending on how many statistics you asked SPSS to generate. I know you are itching to see the output in a hierarchical fashion, but let me first describe and interpret each table from the standard multiple regression output so that it will be helpful when you interpret your own study output. Because I selected descriptives, the first table I will see is the descriptive statistics of all the variables in my model. Now you just want to make sure that the numbers here look reasonable, and they do, and I have no reason to believe these numbers are too extreme. So let's take a look at the correlations table below. If you look at any peer-reviewed journal article that shows results of a regression model, chances are the authors almost always show this correlations table. Why? Because the correlations table is an easy way to detect and show whether there is a collinearity issue which occurs when one independent variable or more is highly correlated with other independent variables. If you see anywhere in the correlations table a bivariate correlation of 0.7 or higher between any pair of independent variables, then you might consider removing one of them or form a composite variable from the scores of the 2 highly correlated variables, because there is a good chance that they might be explaining the same underlying construct. Well, is it bad? Yes. It's because if two independent variables are too highly correlated, what will possibly happen is that they will knock each other out so that neither of them will have a predictive power on explaining the dependent variable. When in fact, both, and if entered separately in a separate model, might have a significant impact on the dependent variable. So if you want to learn more about how or why to form a composite variable, I have a video that explains it in great detail. So I encourage you to check it out, and the link for that video is provided below in the description. Now here I see one pair of independent variables that are highly correlated, and that's between age and tenure. Not surprising, given that as you get older, your time with your organization will also grow. So for the moment, we'll just leave it as it is, and all other correlations here look reasonable. So let's look at the next table. In model summary, you are starting to see some important numbers, and we start with the adjusted R-squared. Well, why not just use R-squared instead? Well, they both identify the percentage of variance on the dependent variable that is explained by the group of independent variables, hence the model. But R-squared tends to overestimate the fit of the linear regression. For example, when you add new independent variables, no matter how unrelated your independent variables may be, when you add them, your R-squared will never go down. It will only increase, but it will never go down. Right now, R-squared here is 0.233. So we multiply this number by 100 to get a percentage term. So this model presumably explains 23.3% of the variation on the dependent variable, which is job satisfaction. Now, as I just mentioned, R-squared tends to be a bit too optimistic, which is why we need to use the adjusted R-squared, because it adds precision and reliability by considering the impact of additional independent variables that might or tend to skew the results of R-squared measurements. With R-squared, when you add new independent variables, R-squared will only go up and never go down. But with the adjusted R-squared, you add new independent variables that really do not add to the predictability of the model, then the adjusted R-squared can go down. Now you can see that the R-squared value has gone down slightly from 23.3% to 22.9%. Now, we know how much of the variation is explained by the model, and we might equally be interested in knowing approximately how much error we're making when we use the predicted values for y based on the regression line instead of the actual values of y. In other words, the standard error of the estimate tells us how far off our estimations of y would be on average. Now let me put it this way. On average, how much do the predicted values of y and the actual values of y in the data differ? That's what the standard error of the estimate tells us. And the number tells us that on average, the actual observed values in the data fall 0.53 units from the regression line. The standard error of the estimate, although rarely emphasized in your stats textbook, you'll almost never see authors in journal articles spending more than a second talking about it. Well, this can actually be more useful to know than the R-squared of the model in some situations. For example, if you're interested in using a regression model to produce predictions, the standard error of the estimate can tell us very easily if the model we are using is precise enough to use for prediction. Intrigued? I bet you didn't expect to hear that. Okay, so for example, let's suppose that we want to produce a 95% prediction interval in which we can predict job satisfaction within 1.5 of the actual score. So to find out how precise our model is, we do a quick math. Given that roughly 95% of the observations should fall within, let's say, plus minus 2 standard error of the regression, we then multiply the standard error of the estimate, which is 0.5366, and multiply by 2, which gives us plus minus 1.07 units y. And since it's less than 1.5, and thus we can claim that the model is precise enough. Now, this is probably more than you wanted to know, but there aren't many books that pay attention to just how to interpret the standard error of the estimate in plain English. So authors often just give a dry technical definition, which would state that it is the square root of the residual mean square. What does that mean? So I hate it when teachers and professors or textbook authors assume that their audience all has already a PhD in statistics. It just amuses me. Okay, sorry for spending a little too much time there. Let's move to the next table in the output. Now, regardless of the value of r squared or adjusted r squared, or how precise your model may be based on the standard error of the estimate reported earlier, whether your model is successful or not, from a statistical standpoint, ultimately you must assess the statistical significance of the result, and we look at this ANOVA table for that. Put another way, the adjusted R-squared provides an estimate of the strength of the relationship between our model here and the dependent variable, but it does not provide a formal hypothesis test for that relationship. So in this so-called ANOVA table, which means analysis of variance, we look at the F-test of the overall significance, which determines whether the R-squared reported earlier is statistically significant or not. The boring and technical description of the F statistic is that it's calculated by dividing the mean square regression 16.523 by the mean square residual, which is 0.288. And we get the F value of 57.377. So in layman's term, the F-test of overall significance indicates whether your regression model provides a better fit to the data than a model without any independent variables. So the F-test for overall significance is basically a hypothesis test where the null hypothesis is that the model with no independent variables fits the data as well as your model, which has several independent variables. And the alternative hypothesis is that your model with several independent variables fits the data better than the intercept-only model, meaning a model with no independent variables. Now, if the null hypothesis is true, you would expect to have the F ratio, the F value, to be about 1 or close to 1 most of the time, although not always. Now, the question then is how high should the F value be for us to conclude that the sample data provides sufficient evidence that our regression model here fits the data better than the model with no independent variables? Well, we'll look at the p-value, which in SPSS is listed in the significance column. Regarding the p-value, if you have a methods textbook, then the author of your textbook will say that if the p-value is less than 0.05, the model provides sufficient evidence to reject the null hypothesis and conclude that your model fits the data better than the null model, which is the one without any independent variables. But why 0.05 as the cutoff value? What's so special about that? Well, nothing really. If we set the threshold p-value as 0.05 and accept that any value below it is statistically significant, then what that means is that the probability of seeing an F value as large or larger than the one observed here, which is 57.377, due to some random chance is less than 5%. And it's commonly agreed in the scientific community that anything below 5% is sufficient enough and genuine enough that we reject the null hypothesis. If the p-value is 0.05 or higher, which means that there is a 5% or higher, that the number we observed is due to random chance, and that 5% is viewed as a little too high. Scientists are willing to be wrong up to about 5% of the time, in other words, being wrong 5 times or less in 100 tries. Because if the probability of observing a number as large or larger than the F value reported here is greater than 5% due to random chance, then that's where we in the scientific community draw the line. Okay, so again, if the p-value here, if the p-value is below 0.05, then it means that the value observed here did not happen by chance. Genuinely, you're likely to see the difference this big or larger quite often. So that's what that means. Other researchers can go for a significance level of 0.01 or even 0.001. But 0.05 is widely used in most academic research, so we'll go with that for the purpose of demonstration. But if you want to be particularly confident in your result, you can set a more conservative level, say 0.01, which is a 1% chance or less or making the wrong conclusion in 1 out of 100 studies. If we find that the p-value is, say, less than 0.001, which is the case here, then there's a really strong evidence against the null hypothesis, because why? The probability of finding a difference as large or larger than the observed value here due to some lucky draw is less than 0.1%. So clearly, this didn't happen by chance. This number is genuine and will frequently occur again and again and again. So that's what it really means when we see a p-value that low. Now, had enough with p-value now? Well, let me give you another way to interpret it using a slightly different language. I promise we'll move to the next table in just a second. I emphasize this because p-value, a lot of people understand this p-value totally differently, which is wrong. So if we assume that the independent variables collectively have zero impact on our dependent variable in the population, if that's what we are to assume, then you would obtain still the sample effect, which is 57.37, or larger effect in about 0.1% of the studies due to random sampling error. But you'll almost never see your textbook stating it that way because it's not as straightforward. Instead, you are more likely to see your textbook saying that there is less than 0.1% chance of making a mistake by rejecting the null hypothesis, which is more straightforward and easier to understand perhaps. So let's move to the next table, the coefficients table. Now, this is a coefficients table in standard multiple regression. We already know how the model is performing here collectively based on the adjusted R-square and based on the F value, which was statistically significant based on the 0.05 threshold. Now, we evaluate each of the independent variables. I don't know if you can see it clearly, so let's zoom in on it a little bit. Okay, that's better. Now, let's interpret one variable at a time. Now, let's start with gender. Just to refresh your memory on how gender was coded in the data, female is coded 1 and male is coded 0. And when you have a binary variable like gender, the size of the regression coefficient, which in this case is 0.03, measures the estimated difference in job satisfaction, which is our dependent variable, between the male workers and the female workers on average. The regression coefficient for gender is negative. So that's how much lower the job satisfaction is on average for female workers because female is coded 1. But looking at the p-value, which is 0.413, and it's clearly bigger than our cutoff value of 0.05. So this estimated difference in job satisfaction between male and female workers is not statistically significant. So there is really no difference in job satisfaction between the two groups. So in other words, you have 41.3% risk of making a mistake by calling the coefficient to be significantly different from 0, which is too high of a risk to be willing to take for us to take. So the evidence here is not sufficient for us to reject the null hypothesis. Now remember that the p-value for each independent variable is really testing the null hypothesis, not alternative hypothesis. Okay, it's really testing the null hypothesis, which states that the variable has no significant impact on the dependent variable, and that anything above the p-value threshold of 0.05 or 5% is viewed as random enough that we can't trust the estimate. Okay, so what about the t-statistic? From a practical standpoint, we don't really try to interpret the t-statistic because we're more interested in interpreting the size of the regression coefficient of each independent variable, simply because that's more exciting than anything else, and in part because t-statistic is used or thought of as a measure that measures how precise the regression coefficient is. Now, t-statistic is basically the regression coefficient divided by its standard error. And if a regression coefficient is large compared to its standard error, then it's usually or probably different from 0. And you can see that here, the size of the regression coefficient isn't large at all when compared to its standard error. So it's no surprise that this estimate isn't very precise and ultimately is not statistically significant. So that's all you need to know for t-statistic. Now let's look at age. Age is a continuous variable measured in years. And we see a coefficient of 0.003, which means that 1 year increase in age, or as people get older by 1 year at any point in their life, I mentioned this because this is a linear model. And whether that 1 year increase happens between 20 and 21 years of age or between 50 and 51 years of age, the impact that 1 year increase in age has on job satisfaction is the same. I know what you're thinking. The concept of linear regression modeling isn't very realistic, I know. But I'll save our discussion of nonlinear and curvilinear regression model for the next time. Okay, so 1 year increase in age is associated with 0.003 unit increase in job satisfaction. But age here is not a significant predictor of job satisfaction as the p-value is very large, clearly above the 0.05 threshold. So we cannot reject the null hypothesis. Now, what about the type of employment? It's a dummy variable coded 1 for part-timers and 0 if full-time. To interpret this coefficient of minus 0.130, this is the estimated difference in job satisfaction between full-time workers and part-time workers, and that part-time workers report on average 0.130 lower job satisfaction than full-time workers because part-timers are coded 1. But the difference between full-time and part-time workers here is ultimately not statistically significant as the p-value associated with it is greater than 0.05, the cutoff value. Now let's keep going. What about tenure? Which measures how many years they have been working in the public sector. So this is public sector employees. The regression coefficient is 0.002, which means that as time spent working in the public sector increases by 1 year, their job satisfaction goes up by 0.002 units. But ultimately, tenure is not a significant predictor of job satisfaction either, as the p-value is greater than 0.05. Lastly, what about PG fit? Now, this variable measures an employee's perception of fit with his or her group or team members. The higher the score, the more it indicates how well they think they fit in with their team or group members. Yes, you can see that it's more like a team compatibility score in a way. So looking at the regression coefficient for PG fit, 1 unit increase in PG fit is associated with an increase of 0.485 on job satisfaction score, and it's statistically significant. Now, if you're taking a stats or methods class at school and you have a textbook for it, then chances are whoever wrote the book will tell you something about the standardized coefficients or simply betas. Well, try never to use it. Avoid ever using it. Why? Well, the authors of your textbook will say that the size of the absolute values of these will enable you to compare which independent variable has the biggest impact, the second biggest impact, and so on. So right now, PGFit has the biggest beta, the biggest standardized value in 0.465. So PGFit has the biggest impact. This is actually an easy comparison because all the other independent variables are not statistically significant, so it's no-brainer. But if you think about it, now forget about the p-value for a second and just concentrate on the betas for a minute. These independent variables are scale-bound, and so they cannot be meaningfully compared with each other. So don't really waste time in arguing that one variable has bigger impact than another and so on, especially when you are comparing two variables with two different measurements. And this is the reason why when you are reading a journal article, the authors almost never talk about standardized coefficients. Okay? Now let's move the table a little further to the right. Now, when evaluating each of the independent variables, another useful piece of information in this table is the part correlation coefficients. In some of the literature, this part correlation may often be referred to as a semi-partial correlation. Now, how is this information helpful or useful? Now, if you square the part correlations, you get an indication of the contribution of that particular variable to the total R-squared. So, it tells us how much of the total variance in the dependent variable is uniquely explained by each independent variable, and how much R-squared would drop if you remove it from your model. So for example, age has a part correlation of 0.019. If you square this, then we get 0.0003, which means age uniquely explains 0.03% of the variance on job satisfaction score. Now, remember earlier that we asked for collinearity diagnostics on our variables as part of the regression procedure. Let's look at the diagnostics column. Now, regarding the two columns under collinearity diagnostics, you would want to know how much of the variability of the specified independent variable is not explained by the other independent variables in the model. So, as a researcher, what you hope to see is that each of your independent variable is unique. And so to do that, you look at the tolerance value. The higher the score here, the more unique each of your independent variable is. But if the values under tolerance value are too small, say values that are less than 0.10, then it indicates that it has relatively high correlations with other independent variables, which might suggest the possibility of multicollinearity. The tolerance values here are all above 0.10. So we have no issues of multicollinearity here based on that. Now, what about VIF? VIF stands for variance inflation factor, and it's just the inverse of the tolerance. So it's 1 divided by tolerance. Now, VIF values above 10 would suggest some concern for multicollinearity, but we have no VIF values anywhere near 10, so we have no issues here. Now, let's check a few more to see if this model meets the basic assumptions of the linear regression model. We'll look at the normal PP plot of regression standardized residual and the scatter plot on the right. Now, in the normal PP plot, what we're hoping to see is that the data points will lie in a reasonably straight diagonal line from bottom left to top right. And that would suggest that there are no major deviations from normality. And it appears that way. Now, in the scatter plot of the standardized residuals, what we're hoping to see is that the residuals will be roughly rectangularly distributed with most of the points concentrated around the value 0. And it does, doesn't it? And if we see some kind of pattern to the residuals, such as curvilinear, like this, then there may be some violation of the assumptions of normality, but we have no issue here at the moment. Now, having said that, it doesn't look like, though, it is totally free of outliers. Cases that are outside of plus or minus 3 standard deviations would be candidates for outliers, and you may not have to do anything if you only find a few in a relatively large data set. Outliers can be checked more formally by inspecting the Mahalanobis distances that are produced as part of the regression that we just ran in SPSS. Remember when I did this and selected these two? Yes. Because of this action that we took earlier, we see 2 new variables in the dataset. Let's first look at Mahalanobis distances. To find out if any of the cases here have a Mahalanobis distance value exceeding the critical value, we look at the residuals statistics table that is generated as part of the regression output. Now, take a look at the maximum value, which is 38.570. To find out whether this maximum value in the data file exceeds the critical chi-square value, we need to look at the list of the chi-square values, which can be found in any stats textbook. And literature suggests using an alpha level of 0.001 and using the number of independent variables used in this model as the degrees of freedom. So we have 5 independent variables, and 5 independent variables with 0.001 alpha level gives us a critical value of 20.515. The maximum Mahar distance value, 38.570, easily exceeds the critical chi-square value, doesn't it? Now, let's find out which case this is in our data file. In the data file, sort the cases in this variable in descending order. Now, should I worry about this case and those right below it? Well, not really. Given the relatively large size of the data, it's not unexpected to have a few outliers like this to appear. So I'll leave this one alone, along with a few others right below it. Now, another information from our output that can be useful in detecting unusual cases is found in the table titled Case-Wise Diagnostics. In a normally distributed sample, you can expect about 1% of all cases to fall outside the range of plus or minus 3 standard deviations from the mean. In our data, we found 9 cases. Now let's look at case number 473. This case, or this person I should say, recorded job satisfaction score of 1. But our model predicted a value of 3.92. Our model clearly did not predict this case or person's score very well, right? Now, what we want to find out then is whether this strange case is having any undue influence on the results for our model as a whole. So we then look at Cook's distance from the residuals statistics table. Literature suggests that cases with values larger than 1 can be a potential problem. In our data, the maximum value for Cook's distance is 0.04, which suggests no major problem. So overall, we don't see major violations regarding the required assumptions of regression modeling. Now, why then would we consider running this regression model in a hierarchical fashion? Well, there really is one major reason why. For example, we already know based on this standard regression model that PG-fit significantly predicts job satisfaction. But you suppose that people may argue that the reason why the perceived group fit, this variable PG-fit, is significant is in part because people with more education tend to work more in teams. So to prove that the variable PG-fit significantly predicts job satisfaction regardless of people's education, you would need to control for it. So along with all the other independent variables here, you also add education in the first step. One more thing, it's very possible that if you work in an organization that promotes learning from coworkers and promotes collaboration between coworkers, then that will surely increase perceived group fit. So to prove that our variable PG-fit is still significant regardless of whether your organization promotes learning and collaboration among coworkers, you want to control for that as well. So we add organizational learning culture, which measures the extent to which organizations promote learning among coworkers. So for you to silence the critics who say PG-fit's impact is largely due to education and organizational learning culture, well, to see the unique and true impact of PG-fit on job satisfaction, we just need to remove the possible effect of education and organizational learning culture. So all we need to do is control for those additional two variables, then see if PG-fit still has significant impact. So we enter PG-fit in step 2. Okay, so let's do that. So here is our dependent variable job satisfaction, and we'll enter these original independent variables and 2 new variables, education and organizational learning culture, in step 1. And then enter PG-fit here in step 2. Now let's run hierarchical regression. The steps are almost the same. We go to regression, as we did before, and go to linear regression. Now move our job satisfaction to dependent and move all of our independent variables except for the last variable PG-fit in step 1 or block 1. It's the same thing. Now click the next button and enter our variable PG-fit in the second step, which is block 2 in SPSS. So this is about the only difference between standard and hierarchical regression in terms of running the procedure. Everything else is almost the same. The only thing that we need to do differently, or we need to add, is in the statistics button. So click that. And the only addition you need to do here is to select R-square change. Everything else is the same. You can just leave it as it is and click continue and click OK to run the procedure. Now, the two tables that we need to focus on are the model summary and ultimately the coefficients table. When we first entered all the control variables in step 1, which is our model 1, the model explained 15.3% of the variance in job satisfaction. And when we entered our main key independent variable, which is PG-FIT, which measures how an employee feels compatible or gets along with his or her group or team members in step 2, then the overall model now explains 26.1% of the variance in job satisfaction. Now, it's an increase of 10.8%. Is the increase of 10.8% in R-squared statistically significant? Is the change or increase in the F value statistically significant? Yes, it is. Now, let's look at the coefficients table. Does feeling compatible with the members of his or her team have a significant impact on job satisfaction, regardless of education and regardless of people, whether the organization promotes culture, learning culture? Absolutely. To those of you taking stats class at school and learning to use SPSS and to interpret SPSS output, I hope this video was helpful and I hope to see you next time.